We discuss a uniformly charged disk, and specifically we would like to calculate the electric potential due to a uniformly charged disk, and using that calculate the electric field everywhere on the axis of the disk. Before we proceed, let's have the idea that we are going to build this disk using rings. So let me draw a ring first, and the charge on a ring, if it is uniformly distributed ring, we can define what is a charge per unit length. So let's say this is lambda, which is charge per unit length. Let's say the total amount of charge on the ring is q ring, and the charge per unit length will be 2 pi times r, where r is the radius of the ring. So this being the center, we have this is r, and this will be the s. This could be d phi. Since it's a uniformly charged ring, whether I talk about the total ring or part of the ring, the charge density is the same. So this is also the total charge in this tiny segment of this ring will be dq over the arc length, which is ds, where ds is equal to r times d phi, because that's the relation between the arc of a circle with respect to the radius. Think of it as the circumference of a circle being r times the total angle of the circle is 2 pi. So 2 pi r gives you the total arc length of the circle. So in that sense, this is also equal to dq over lambda, sorry, r times d phi. So that's for a ring. If we were to do this for a disk, so that's a disk, but I want to build this disk using rings of finite length. So let's actually, oops. So let me try to build this using circles. So that's one, and oops, no, that's better. And now we are interested in, so if this was a center, a tiny element of the ring would be the shaded region in here. In the infinitesimal limit, even though this looks like a trapezium, not even a trapezium because there are curved lines in here. But in the infinitesimal limit, this is pretty much a rectangle, and its area would be ds times dr here. If the radius is r, there's a tiny element dr there. Again, use the same idea. Now we have uniform charge density, but now it is charge per unit area. So if the total charge on the disk is q, so this is q of the disk now, divided by the area of the disk, if the total area radius is r, so that's pi r square. So this is a small radius r of the ring at this point, and the disk is built, let's say this is the bigger disk that you build, and this is R. That's the total length of the disk. So you build it using this small, tiny line element, which has been exaggerated with its width of the ring. But the area of the disk is pi r squared, so the total charge on the disk divided by the area is charge per unit area. If it's a uniformly charged disk, then it doesn't matter which area we are talking about. We can also talk about the shaded region, and there we say this is dq again over charge over area, where area is now r times d phi. That's your ds times dr. Dr here. These two give us the connection. Like if I were to relate the two, it is easy to see that lambda is the same as sigma times dr. That's a connection you want to build when you're going from a ring to a charge. If you're talking about a ring, you talk about charge per unit length. You're talking about a disk, you talk about charge per unit area. The connection between the two is lambda is equal to sigma times d. With that connection in mind, we can proceed to calculate the electric potential. So the electric potential a due to a ring. So let me draw a diagram here. So that's here. So this we have, and somewhere along the axis of the disk gets contribution from every point on this disk, which is having a radius r, and on the axis a distance x from the center of the disk is this point here. This forms a right triangle, so, and the distance here is x squared plus r squared. And this tiny element here, which is a element of an arc, has dq, charge dq. Each tiny element on the disk is equidistant from the point of observation, so we can say the electric potential due to a ring will be equal to integral of all these tiny electric potentials from each of these arc lengths on the circle. That's dV here, and that's equal to an integral k dq, the contribution from every tiny element, divided by how far each element is from the observation point, and they are all equidistant. So it's x squared plus r squared. Since they are all equidistant, this is the same as k times k over x squared plus r squared over integral dq. But the total charge on the ring is q times ring, right? So this is k times q of the ring divided by x squared plus r squared, where r is the radius of the ring. Q ring, we said, is lambda times 2 pi r. So replace that. So now we want to build a disk out of this. When we say the electric potential due to a disk, we are building it out of electric potential due to rings. So adding up all the rings, and that goes from r equal to 0 to r equal to capital R, where capital R is the radius of the disk. That's equal to, we want to write this as an integral 0 to r k times q ring is lambda times 2 pi r, but lambda itself is sigma times dr. So it is 2 pi r times sigma times dr. So where we have used the fact that Q ring first is lambda times 2 pi r. Lambda itself is sigma times dr. So that's the total charge on the tiny element. So this is this element here that's forming a structure contributing to the disk, divided by the distance. Now since the integral is over r, we have to do this integral. A substitution that helps for this integration is t is equal to x squared plus r squared, and that leads to dt is equal to x being fixed in this integration is 2 times r times dr. 2 times r, that's the differentiation of r squared. We also need to know that when r is equal to 0, t is equal to x squared, using this relation here. And when small r is equal to capital R, then t is equal to x squared plus capital R squared. Using this relations, we can do this integral. We have 2 times r times dr, which gives you dt. So let me take out a k and a pi and a sigma. This is k, pi, and a sigma. K itself is 4 pi epsilon naught, which I'll start writing in the next step. So it's 0 to r. 2r dr is dt. Oh, I should also replace my limits and do this element. So the lower limit in terms of t is x squared. And the upper limit when r is equal to capital R is x squared plus r squared. Rewrite the rest in terms of dt, so that's dt over square root of t. Integral of this is 2 times square root of t, so let me write this as pi times sigma divided by 4 pi epsilon naught, because k is 4 pi, 1 over 4 pi epsilon. The integral of square root of 1 over square root of t is 2 times square root of t, because square root of t is t raised to minus half. Integration leads to raising the power by 1, and whatever power is got is put in the denominator also. So that's 2 times square root of t. But that has to be evaluated at x squared plus r squared and x squared, which gives us, so 2 pi and 2 pi cancels out, so it's sigma over 2 epsilon naught, and we have square root of x squared plus r squared minus x. That's the electric potential due to a disk on the axis of the disk. So by axis, we mean along this line. The electric field, the x component of the electric field, is minus of the derivative of the electric potential with respect to x, and we are talking only about the axis. And that leads to since it is a negative sign, so this negative sign becomes plus. So it is sigma over 2 epsilon naught. It's 1. And the first term gives you, that is a minus sign to begin with, and that is a factor of x in the numerator got by differentiating the argument of the square root, and the power of the square root goes as 1 by 2 minus 1, which is minus half, which takes the whole thing in the denominator. And that's the expression for the electric field that we have to. We also have some limits, interesting limits that we can look at. We are talking about a positively charged disk. So if I were to look at the disk alone, so there is a radius r and it's positively charged. And that's a radius r of the disk. When I'm very far away from the disk, let's say x, that's extremely far away from the disk, it is going to look like a point charge. When you're extremely far away from a positively charged sphere, the sphere is negligible in size and it will look like a point charge. So, and we do know that the electric field of a point charge is kq over r square, here r being the distance x in this case. So that should show up here. So how does that come out? So let's say x is significantly larger than the radius of the disk. And in that case, the electric field, x component of the electric field is sigma over 2 epsilon naught. And this is 1 minus, I should write this as x over, take the x out, and whatever is remaining is 1 plus r square over x square. That cancels away the x. And once you have an expression like 1 over 1 plus, let's say r square over x square here, the square root can be written as the power of half, and the series expansion for this is 1. The power of this, when it goes in the numerator, is minus half. And whatever is the term uh, in the denominator, so that's r squared plus x squared. And there are higher terms in this, which we don't have to keep because this is so small. When you square it, it's going to be further small, so we don't have to keep that. The 1 here cancels with this 1, the negative sign cancels, so what we have is sigma over 2 epsilon naught, and that is a factor of 2, and that is r squared over x squared. It still doesn't show up as a point charge, but we can provide a pi here. So multiply by a pi and divide by a pi. And then we see that there is a 4 pi epsilon naught. Sigma times pi r square for a disk is nothing but the total charge on the disk. So that's equal to q, or k times q over x squared, where this is the charge on the disk, which is exactly how it would look like if you're very far away. That's the electric field due to a point charge. So that's correct limit. Similarly, let's do this for the opposite limit. When you're really close to a disk and you're on the axis of the disk, x is significantly small compared to the radius r. In that case, you can immediately drop the r in the denominator. No, not the r. You can immediately drop the x in the x in the denominator. In fact, you can even drop the, now after you drop the x in the denominator, it is x over r that remains, which is again small compared to 1. So this is simply Ex is equal to sigma over 2 epsilon naught, which is of course the electric field due to a uniformly charged plate of infinite extent. And that's exactly what we mean by infinite extent, that we are too close to the plate and very much at the center of the plate too, that extreme sides of the plates are not playing a significant role in that region. The electric field is a constant, and it's decided by simply the charge per unit area on the plate. With this, let me stop the recording.